up to now, we have been dealing with chemical equations that represent the overall reaction that occurs. In other words, it's showing us what reactants we start with and what products we end up with. But what it doesn't show us is the actual pathway. How do we get from those reactants to those products? And the thing to realize is that this can occur in different ways. So that's why in talking about determining reaction rates, that they are determined experimentally when we're talking about this overall chemical equation that really represents a summary of this reaction. So what we're going to look at now is the individual steps that occur, that when we sum them all together, we get these overall chemical equations. Okay, so a mechanism is the series of steps by which the reaction occurs. And again, realize that the chemical equations that we deal with, these are summaries, in essence, of what's happening with all those steps. Okay, these reaction mechanisms, they are determined experimentally, and but we can represent them with a series of small chemical equations, and we call these elementary steps. And elementary steps, the thing about them is that their rate law can be written from the chemical equation. In other words, it really does represent exactly what is happening, what collisions are taking place. And so we can write the rate law of an elementary step from its chemical equation. So a couple of terms that we'll use in talking about mechanisms. An intermediate, that is a substance that is formed in one step and used up in a subsequent step. So if you remember when we were doing Hess's law and how when you add up reactions, if you have something that's the same on both sides of the equation, that it cancels, well, that's what happens to intermediates. We don't see these in the overall reaction. We would only see these in the elementary steps. Molecularity is a term that's used to indicate how many reactants need to collide for that elementary step to occur. So let's take a look at an example here. Here we've got ozone decomposing into oxygen molecules, and it proposes a possible step here, or a possible mechanism that consists of these two steps. And so here's my two steps. Let me make it red. Okay. And let's look at what's happening. So in the first step, the ozone is going to decompose into one oxygen molecule and one oxygen atom. Then in the second step, another ozone interacts with a single oxygen atom, and we get two oxygen molecules. Okay, so there's a potential way that when we add these things together, all right, so what happens when we add them together? Well, we get 2O3. We have an oxygen on our product side, an oxygen atom on our reactant side. So those are going to cancel out, which means that's an intermediate. We produce it in the first step, and then it gets consumed as a reactant in the second step. And then we add these together, the oxygen molecules, and we get 3 oxygen molecules. So this mechanism does add up to give us the initial equation that we were talking about. Okay, let's see if there's anything else. Okay, in looking at mechanisms, there are two criteria that have to be met in order for it to be considered a valid mechanism for that reaction. One we looked at just a minute ago is that the elementary steps have to add to give the overall balanced equation. Then the second one we're going to look at now is that the rate law of the slow step has to agree with the actual rate law. Okay, remember we said elementary steps, we can write their rate law from the equation itself. So when we do that, for the slow step in the mechanism, we should get the rate law for the overall reaction, which is, again, determined experimentally. Okay, so what is this deal with the slow step? All right, when we have a series of steps, okay, each step is occurring at some rate. It each has its own rate at which it reacts. And so if you think about it, if we have a sequence of steps and we're looking at what is the rate of the overall series of steps, that rate is going to be limited by the rate of the slowest step. So in determining the rate for the overall reaction, we want to look at the slow step in the series. And so here's a kind of a picture representation here we have a two-step reaction here, or two-step mechanism, and the second step is the slow step. And so you can see here that the reactants would be coming in, and we sort of visualize it as this fast step here allows a certain flow of these reactant particles through, and the slow step would be like constricting the flow to where only a few at a time can get through there. So the overall rate from reactants to products is going to be limited by that slow step. And also then, if we experimentally determined the rate for this overall reaction here, we would expect that if I wrote the rate law for the slow step there, that it would match up to the experimentally determined rate law for that. There is a handout. Let's see, in your book it talks about finding the rate law based on the slow step. And I think in the text that we use, it primarily focuses on the slow step being the first step. Okay? But I have a supplementary handout that is on the website that steps you through the process of determining the rate law when the slow step is not the first step. And let me just, with this example up here, the reason that you have to do a little bit of extra work with that is, look at this slow step here, all right? What's our rate law? If we wrote the rate law for this, we would write that rate is equal to some rate constant, and then we have N2O2 and O2. Okay, well, what's the problem with that? Well, right here it is. We've got an intermediate in our rate law. Can't have that. We can't have something in our rate law that isn't in the overall reaction, because there's no way that our experimentally determined rate law would match this rate law for the mechanism. So we have to do a little bit of extra work, and I'm not going to, for time's sake, I'm not going to go into that right now, but you do have a handout that will step you through the process and some practice problems with the key, with everything worked out. So take a look at those, and then we'll go over that some in class as well, of how to determine the rate law when the slow step is not the first step. Okay, we talked a little bit about the collision model. Again, just to reiterate that the reactions occur when reactants collide and they collide with enough energy for the reaction to occur. And so, starting out with this, one of the things that was observed is that not every collision, even at the appropriate energy, results in a reaction. And so we have this model that kind of takes that into account. It takes into account the energy of the collisions and that the fact that still not every collision will result in a reaction, even if they're at the same energy. And that is called the Arrhenius equation. And so this is kind of what's happening here, or how it's taking this all into effect. We talked about the fact that if we have low kinetic energy or not enough kinetic energy, which means less than the activation energy, that like in case B here, they'll just collide and no reaction will occur, whereas in case A, if we are above the activation energy, we're going to get a reaction. Okay, and let's look at, here's our kind of the temperature profile, meaning at low temperatures we have a narrower distribution of particles, this blue line here, whereas at higher temperatures we see a broadening of the distribution of particles. And so you can see here how if this is our activation energy, they're calling it E minimum, but activation energy, and see we have a lot more particles that meet the requirements, the energy requirements for a reaction to occur at higher temperatures. And the other thing to observe is that the increase in the number of particles that meet that criteria is not linear either. Okay, you can kind of see that from the graph. All right, here is a reaction profile, and you'll be doing, I think, some problems with this. So, and we've seen these before. So this is my potential energy. If it's endothermic, we would expect to see, get my pen, different color here. We would expect to see reactants lower than products. Okay, endothermic. As it goes through the reaction, the particles gain energy, gain potential energy. All right, here is our activation energy. The activation energy is measured from the reactants up to the top of that peak. Okay, so this would be the activation energy for the forward reaction. If I'm looking at the reverse reaction, in other words, converting the products back into the reactants, then the activation energy goes from the level of the products up to the peak. Okay, and then the same thing here. This is a really good slide to put in your notes. It lays kind of everything out, and you'll be doing some quantitative problems with these reaction diagrams here. Okay, so back to the Arrhenius equation here. All right, so we have to have enough energy, activation energy, to produce the reaction. And here's the other thing. The orientation of the reactants have to allow formation of new bonds. In other words, they have to collide in the right positions. And the way we're going to take care of that is this thing called a frequency factor. All right, so let's look at what this means. Here we have, there's a zone within our iodine molecule here where, iodine and hydrogen. Okay, so in order for this reaction to occur, the chlorine needs to connect with the hydrogen, not with the iodine. And so we have this little area here where we would have a successful collision, and then this fairly large area around here where if it collides from that direction, we aren't going to get a reaction. Okay, so this is what we mean when we're talking about a frequency factor. A frequency factor takes into account the geometry of the two interacting species and then figures out what fraction of collisions would actually be successful. Okay, so here is the Arrhenius equation. This is probably the most useful form, the one you'll use the most of it. I do not believe that is in your, I think this is the form that it's on your sheet, your equation sheet for the AP exam. But remember, you can derive this one from the other using the fact that in either case, at any temperature, if I'm changing the temperature of it, that this piece here will be the same. For the same reaction, the frequency factor is going to remain the same. So those will be equal, and that's going to tie the two equations. If you have a K1 and a T1, your A is still going to be the same. So you can derive this equation here. If you don't have it memorized, you can derive it from this first equation, which I believe is the form that it's on the formula sheet. Okay, so here is an example of how we would use this. How much faster is a reaction if the temperature is raised from 25 to 35 degrees Celsius when activation energy is 58.1 kilojoules per mole? So how much faster? That is basically asking me for this ratio, the ratio of K2 to K1. Okay, so that is going to be our unknown here. Our activation energy is 58.1 kilojoules per mole. Now, our R value in here is the 8.3145, and that's going to be joules per mole Kelvin. All right, so we need to either convert that into kilojoules, or we can just get in the habit of writing your activation energy in joules in this equation. And we need our, let's see, so we want 1 over T1 is 298 minus 1 over T2 is 308. Okay, so we get, if we pull all that together, so I get that the natural log K2 over K1 is 0.761. Okay, so to do the inverse of the natural log, I'll get that K2 over K1 is equal to e to the 0.761, which is equal to 2.14. So raising it by 10 degrees basically doubles the reaction rate. And actually that is the rule of thumb for reaction rates. If you increase the temperature by 10 degrees, you should get around a doubling of the reaction rate. Okay, now as we did with the first order, second order, the integrated rate laws, we can do the same kind of thing with the Arrhenius equation. If you look at it, it's in the y equals mx plus b format. And so if we plot natural log of k versus 1 over the temperature, we can find activation energy, right, which is a pretty common thing to be asked to do. So let's look at this data. All right, I've already put it into my thing. So if I do a linear, if I do a linear regression, and mine are in, I believe, L3, and L4, let's see. Okay, and so I'm getting a slope is minus 370 or 3729.6. Doesn't want the, let's see, the other thing I can find from that, my intercept is 8.97. Okay, so we get our slope is minus EA over R, right? And so the slope times minus R is equal to EA. R is 8.3145. So minus 3729.6 times 8.31. I'm getting an activation energy of about 31 kilojoules, right around there. And then if we needed the frequency factor, the intercept is equal to the natural log of the frequency factor. So we do inverse natural log of 8.97. We get a frequency factor of 7.863. Okay. Catalyst, a substance that speeds up a reaction without being consumed. One of the things, and I forgot to mention this when we were talking about reaction mechanisms, is you will also see catalysts showing up in your reaction mechanism. And the way you're going to identify those is that they are sort of the opposite of the intermediates. Remember how we said intermediates are produced in one step and then consumed in a subsequent step? Catalysts are going to show up on the reactant side first of one of the steps, and then they will end up as a product at the end, totally unchanged. Okay, so it's still going to cancel out, but it's just that the catalyst will show up first as a reactant, then as a product, whereas intermediates show up first as a product, then as a reactant. Okay, and again, relating enzyme is biological catalyst, essentially. And let's look at what catalysts do. Up to now, we've just said, well, they speed the reaction up. Yes, they do, but how do they do that? What they are doing is providing an alternative path, an alternative mechanism, if you will, for the reaction to occur, and this alternative path has a lower activation energy. When I lower the activation energy, I increase the number of collisions that are capable of producing a reaction. Okay? Remember our temperature profile. So I'm just moving that activation energy down, which means I'm going to have a greater area under that curve, which means more particles colliding to produce successful reactions. And so here's kind of a drawing here of how it changes our reaction profile. Also on this slide, it talks about two different types of catalysts. A homogeneous catalyst, that's the same phase as the reactants. Meaning if I have a liquid, I might add a liquid catalyst to it. So same phase as the reactants. A heterogeneous catalyst is one that is in a different phase. Okay, these are probably, the heterogeneous ones are probably ones that you are most familiar with in your everyday life. And I say that because, I thought I had a picture there. Oh, well, I say that because you have a catalytic converter on your car. Catalytic converter is a heterogeneous catalyst. It's got a solid plate that's in there, and the reactants that it's catalyzing, or the total reaction it's catalyzing, reactants and products are gases. Okay, so heterogeneous.